This is section 3.4, concavity and the second derivative test. We've seen that locating the intervals on which a function f increases or decreases helps to describe its graph. In this section, you'll see how locating the intervals on which f prime increases or decreases can be used to determine whether the graph of f is concave upward or, curving upward or curving downward. Let f be a differentiable function on an open interval I. The graph of f is concave upward. Looks like this. Looks like if it's a cup, it would hold water. It's called concave upward. On the interval I, when f prime is increasing on the interval. So when f prime is increasing. Well, as we saw before I get to that, let's make sure that that makes sense. So if I start here on the left someplace and I draw a tangent line, I can guess, for example, that that slope is, -2. And then I move to the right, pick another x, draw that tangent line, and I might guess that that slope is, -1/2. And later yet, pick another place, and the slope there is 0. And so as I'm moving left to right on this graph, the slopes are increasing. Say this is slope 4 or something. And for the slopes to increase, that means that f prime, which gives you the slope, is an increasing function. And so the implication is that for something to be increasing, its derivative, so the derivative of the first derivative, will be positive. That's what increasing of a function means, is its derivative is positive. Well, what is the derivative of the first derivative? Well, that's the second derivative. So if the second derivative is positive, that's going to imply that f is concave upward. And that's the abbreviation we'll use for concave upward. Okay, concave downward looks like this. So this is some function f. Let's look at, what's happening to its derivatives as we move from left to right. So let's say that slope is, 3. And then this slope is 1 maybe. And this slope is 0. And this slope is -3. So what's happening as we move from left to right? Well, the slopes are decreasing. That is, f prime is decreasing. And so if you look at the item I was reading a second ago, the definition of concavity, where I said concave upward on the interval when f prime is increasing on the interval, and concave downward on the interval when f prime is decreasing. Excuse me. And for a function to decrease, its derivative, its first derivative, must be negative, which means that the second derivative function must be negative, and when it is, f will be concave downward. And that's the abbreviation we'll use for concave downward. Okay. Another thing that's true about concavity, and I don't know how well I did those drawings, but look at all the tangent lines. When a function is concave upward, in every case, the tangent lines lie below the curve. Like this one right here is below the curve. All of its y values, except for the point where they intersect, have lower y values than the curve y values. And over here, when it's concave downward, the tangent lines lie where? Right above the curve. And so sometimes that's a helpful thing to know, that all of the y values on that line, except for the point of intersection, are greater y values than the curve. So if you're trying to figure out if something is concave up or concave down, this location of the tangent line might help you to make a decision about if it's concave upward or downward if you're looking at a graph. Okay. So to do this, this is going to look a whole lot like what we did with the first derivative and intervals of increasing and decreasing. So if we have a function, f of x equals 1/3 x cubed minus x and if we were to look at the graph of that, which is on figure 3.24, if I copied that, I hope I did. Well, even if we didn't, you can graph that and look at that function. And its derivative, which is 3 times 1/3 is 1x squared minus 1. If you look at the graph of the derivative, which this is a pretty easy one to graph, it's just a parabola that's been shifted down 1. So let me set this up. Oops, those marks are not spaced the same way. There we go, that's a little bit better. Okay, so that function is going to go like this. Oops, made that one too high. Pretty close, but not quite right. Okay, so that's what the derivative looks like. And I made this an easy one so that you can really look at it closely. This function is decreasing on the interval from -infinity to 0. And it's increasing on the interval from 0 to infinity. So what that means is that if you looked at the graph of y equals f of x, which looks something like this. Let's see. Dang it. Didn't do a good job. Let me try again. If you look at that graph, the left-hand side of that graph looks like if that were a cup, it would be pouring water out. So that would be concave downward. from negative infinity to 0. And the right side of that graph looks like it's concave upward. If it were a cup, it would be holding the water from 0 to infinity. And so you can see the relationship between those two. I hope that when the first derivative graph is decreasing, which means f prime prime will be negative, then this graph will be concave downward. And when f prime is increasing, which means its derivative f prime prime, f double prime, is positive when f prime is increasing, which means f double prime will be positive when it's concave upward. Okay, so it's just a little bit of visual representation of that. So let me show you what we'll do with this, because the representation I have here is to help you understand why, if the first derivative is increasing, that the function will be concave upward, and when f prime is decreasing, the function is concave downward. And again, this is the graph of f itself, just so you realize. Okay, so what we would do to continue this would be just like the first derivative number line analysis gave us information about the increasing and decreasing behavior. The second derivative number line analysis will give us information about concavity. So, just like what we did with the first derivative, we're going to set it equal to 0. We're also going to consider if f double prime of x doesn't exist. And of course, 2x exists for all real numbers, so the fact that it fails to exist never happens. And over here, x equals 0 is what that would solve for. And so here's the second derivative number line test. We got the answer of 0 from setting equal to 0. So we put a solid dot there. We label this with the second derivative, and this is why I want you to be careful about labeling, is because we have both first derivative number line analyses and second derivative number line analyses. And if you're solving an inequality, you'll even have a function number line analysis, which is possible. Anyway, so if I were to pick a number to the left of 0, like negative 5, and put it in to this first derivative function, if I put in negative 5, 2 times negative 5 will give me a negative answer, so negative. And if I put in something to the right of 0, like 6, 2 times 6 is 12, which is a positive answer, so I'll put a positive here. And what that tells me about the function is, if the second derivative is negative, we'll write concave downward. And if it's positive, we'll write concave upward. And so our conclusion would be, if they ask us for the intervals of concavity, so that would be the question, find the intervals of concavity. Then our answer would be f is concave downward on the interval from negative infinity to 0, because f double prime is negative on that interval, negative infinity to 0. By the same token, f is concave upward. I'm using those little marks to mean same thing as above, on the interval from 0 to infinity, because f double prime is positive on that interval 0 to infinity. Okay. So that's how you would do this. This is a second derivative number line analysis, and it's very much like what we did for the first derivative number line analysis. So Theorem 3.7 is going to kind of wrap all this up in a nice package. Let f be a function whose second derivative exists on an open interval I. If f double prime of x is positive for all x in the interval, then the graph of f is concave upward on that interval. If f double prime of x is less than 0 for all x in the interval, then the graph is concave downward on that interval. Okay? So, again, we're going to do, like we did for this first derivative number line analysis, find out where the second derivative is equal to 0, and where it doesn't exist. Those will give us important numbers. We don't call them critical numbers. That's a word reserved for first derivative equals 0 or first derivative doesn't exist. So there are these important numbers, if you will, that we'll find, put them on the number line, do the number line analysis. Negative values tell us concave downward, and positive values of the second derivative indicate concave upward for the function. All right, so that's what we will do. So let's look at example 1. F of x equals 6 over x squared plus 3. Okay. So the question is determine the open intervals on which the graph of f of x is concave upward or concave downward. All right. So f of x is continuous on the entire real number line because there's no number x that would make me divide by 0, at least no real number x. And so we will find the first derivative. Since that's a quotient, I guess we can use the quotient rule as is. So low d high, the derivative of the constant 6 is 0, minus high d low, the derivative of x squared plus 3 is 2x, all over the square of low. That's x squared plus 3, quantity squared, which simplifies to be negative 12x divided by x squared plus 3 squared. Now, if we did the first derivative number line analysis, we could find out where this function is increasing, where it's decreasing, where it has a relative max, where it has a relative min. That's not what we were asked to do, but we could do that. Going on to the second derivative, again, we have a quotient, so let's use the quotient rule. Low d high, the derivative of negative 12x is negative 12, minus high d low, and the derivative of something squared is 2 times that something to the first power. Oops. Put the 3 in the wrong place. To the reduced by 1 power times the derivative of the inside function, which is 2x, all over the square of low. Okay, so let's do a little bit of simplification. What I'm not wanting to do is that squaring, so I'm trying to avoid that. Minus a negative, so that'll be plus. Let's see, 12x times 2 is 24x, times 2x is 48x squared, right? Times x squared plus 3. I'm also not wanting to do that distribution, at least not yet. And then power of a power, you multiply the exponents. 2 times 2 is 4. So this will be x squared plus 3 to the 4th. All right. Then, looking at those two numerator terms, there is a common factor of negative 12. No power of x is a common factor, but x squared plus 3 to the first, the lower power, is a common binomial factor. So if I factor out negative 12 and x squared, a single x squared plus 3, it will leave the other x squared plus 3. Plus, then 48 divided by negative 12 is negative 4. X squared divided by x to the 0, I guess, is x squared is still inside. And x squared plus 3 divided by itself is an understood times 1 back there behind the x squared. All over x squared plus 3 to the 4th. Well, one of those x squared plus 3 can definitely be canceled. So when that cancels out, I'll have only 3 of them in the denominator, leaving negative 12, and then inside x squared minus 4x squared is negative 3x squared plus 3, which has a common factor of negative 3. And if I pull that out, negative 3 times negative 12 is 36. That will leave positive x squared minus 1 over x squared plus 3 cubed. And then that factors to be 36 times x plus 1 times x minus 1 all over x squared plus 3 quantity cubed. And you do want to get that simplified and in factored form because we're about to set that equal to 0, just like we did with the first derivative. This is the second derivative. We set equal to 0. We also consider if there's any number x that would make the second derivative fail to exist. There is no real number x that if you were to square it and then add 3 that you get 0. So that never happens. Okay. Then the only way a fraction can equal 0 is if the numerator equals 0. So the whole fraction will equal 0 when the numerator itself is equal to 0. And that occurs when x is negative 1 and positive 1. So, do our number line analysis. Negative 1 was obtained by setting the second derivative equal to 0. So I put a closed dot, and also at 1, that same thing happens. I have no numbers to put on the number line analysis because of the second derivative failing to exist, because it never happens. Okay. So, this is the second derivative number line analysis, and it will give us information about the behavior of the function f on the same intervals. So, let's see. Pick any number to the left of negative 1. Well, let's do negative 2. 36 is always positive. I'm looking at this version right here of the second derivative for my substitutions. Negative 2 plus 1 is a negative number. Negative 2 minus 1 is a negative number. Divided by x squared. See, negative 2 squared is positive 4. 4 plus 3 is 7. 7 cubed is a positive answer. So positive times negative divided by positive is positive, which means that the function from negative infinity to negative 1 is concave upward. Now pick a number between negative 1 and 1, like 0. Let's do that one. 36, of course, is positive. 0 plus 1 is positive. 0 minus 1 is negative. 0 squared plus 3 is 3. 3 cubed is 27, which is positive. Positive times negative divided by positive is negative. So between negative 1 and 1, the function will be concave downward. Now let's pick something to the right of 1, like 3. 36 is positive. 3 plus 1 is positive. 3 minus 1 is positive. And 3 squared is 9, plus 3 is positive, cubed is still positive. Positive times positive divided by positive is positive, which means that the function is concave upward from 1 to infinity. Okay, so I've said the answer. We now need to write it down. It's all right there in the second derivative number line analysis. We just need to convert that to words. So f is concave upward on the interval from negative infinity to negative 1, as well as, so union, from 1 to infinity. And why do we say so? Well, because, again, this has to be a calculus reasoning, because the second derivative is positive on those intervals. Okay, then f is concave downward on the interval from negative 1 to 1. Why do you say so? Because the second derivative of f is less than 0 on that interval, negative 1 to 1. All right, so there you go. Looks a whole lot like the first derivative number line analysis. And again, they set this up in a table, which is fine. It's not my preferred way of doing this, but you can do that. And then if you plot this graph in your calculator, it's just for basically confirming what we're seeing in our analysis. It goes like this, and like that, like this. So it's concave upward here, concave downward there, and concave upward there. All right, so if you look at the graph, that certainly is pretty clear, clearly what's going on. Now, for most of our examples so far, we have yet to see either one in the number line analysis where the derivative fails to exist. That's because we've had continuous functions. And so we're going to now turn to an example where that's not necessarily the case. All right, so when we did the first derivative number line analysis, we found out that there was a special occurrence when the first derivative changed sign. So when the first derivative went from positive to negative, that gave us a local maximum. And when the first derivative went from negative to positive, that gave us a local minimum. Well, is there something like that when the second derivative changes sign? Well, actually, there is a special point. Let's just draw a few curves, generic curves, if you will. If we have, for example, a curve that looks like this, concave upward, then concave downward, at that point where it changes from concave upward, that means the second derivative is positive, to concave downward, which means the second derivative is negative, there's a point, and that point is called a point of inflection. And it doesn't matter whether it's changing from negative to positive or positive to negative. It's just a sign change in a sign change in the second derivative at a point that exists on the curve. So it actually has to be a defined point on the curve. To be a point of inflection, there has to be a point on the curve. Here's another. This is concave downward until it gets right here. Then it changes to concave upward. And there's another point of inflection. Again, the second derivative is changing sign. In this case, it's going from negative to positive. And even this one let's draw this carefully. If we had a graph that looks like this and like this, this one happens to be concave upward here and concave downward here, and that's a point of inflection. So all three of these are points of inflection. One other thing that's interesting to note is if you draw in the tangent line, that's a place where the curve crosses through its tangent line. Here it's on the left side of the line, over here it's on the right side. Here on this side it's below the curve, here it's above the curve. Here it's to the right of the curve, and there it's to the left of the curve. So another way to talk about point of inflection is when the graph crosses its tangent line, you'll have a point of inflection there. So the definition of the point of inflection: let f be a function that is continuous on an open interval, that's very important, and let c be a point in the interval. If the graph of f has a tangent line at the point cf of c, then this point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or from downward to upward at the point. And so if you go to Theorem 3.8, that definition is almost a pre-calculus definition, because it's not talking about derivatives or anything, although continuity is mentioned, and that's important. So if we want to locate the possible points of inflection, like we did with the first derivative, we'll determine the values of x for which the second derivative equals 0 or the second derivative doesn't exist, very much like what we did for the first derivative number line analysis. All points of inflection are, according to Theorem 3.8, things that if c comma f of c is a point of inflection on the graph of f, then either f double prime of c is 0 or f double prime of c does not exist. And again, the fact that f double prime of c is 0 or doesn't exist doesn't mean you will definitely have a point of inflection. It just says it's possible. Okay, so let's do an example of this, because that's really where I think you understand the best, is when you see an example. So let's look at this one. F of x equals x to the fourth minus 4x cubed. And we're supposed to determine the points of inflection and discuss the concavity of the graph. So I'd like for you to start on this and see how far you can get. So pause the recording and come back in a minute when you get stuck or when you think you're done. We'll look at your answer. So since we have both a first and second derivative test, I might want to indicate that you could accidentally do a whole bunch of work that's not asked for. And so when the discussion is about concavity and points of inflection, go to the second derivative. If the discussion is supposed to be about where the function increases, decreases, and where the relative extrema are, that's the first derivative. So this question is definitely about points of inflection and concavity, so we need the second derivative. Of course, to get there, we're going to go through finding the first derivative, but only as a means of getting to the second derivative. So the second derivative of this function is 12x squared minus 24x. So to find the important numbers, we set that equal to 0, or when the second derivative doesn't exist. And for this polynomial, that never is a problem, never an issue. So the second derivative exists for all real numbers x. So over here at equal to 0, the common factor is 12x. Factored out, that leaves x minus 2. And so this equation solves to give us 0 and 2 as important numbers. Again, we don't call them critical numbers when it's the second derivative. Okay, so put those numbers on our number line analysis. They both came from equals 0, so put great big dots on those. Label this as the second derivative number line analysis above, and what that means about the function below. And that separates the domain into 3 chunks, and so we need to talk about the behavior of each one of those chunks by picking numbers in each chunk to represent the rest of them. I'm going to use this version of the second derivative for my substitutions. So I could put in a number like -1. So 12 times -1 is negative. -1 minus 2 is -3, so that's negative. Negative times negative is positive. Between 0 and 2, I might pick 1. 12 times 1 is positive. Times 1 minus 2 is -1. So positive times negative is negative. And then finally, maybe 3. 12 times 3 is positive. 3 minus 2 is positive. Positive times positive is positive. So that second derivative value tells us that the function f is concave upward from -infinity to 0, concave downward from 0 to 2, and concave upward from 2 to infinity. So we will write what we just realized. F is concave upward on the intervals from -infinity to 0, as well as from 2 to infinity, because f double prime is greater than 0 on those intervals. Okay, so this is where I'm addressing concavity. On the other hand, f is concave downward on the interval 0 to 2. Again, why? It's because f double prime is negative on that interval. Okay, so we've addressed concavity. The other part of this question is points of inflection. So anytime there's a sign change in the second derivative for a point that's on the curve, and of course f of x, the original function, is continuous on its whole domain because it's a polynomial, so that means that f has a point of inflection when there's a sign change in the second derivative. So it has a point of inflection at x equals 0 and at x equals 2. Why do we say so? Because f double prime changes sign at x equals 0 and x equals 2. And again, it's not important whether it goes positive to negative or negative to positive. Just doesn't matter. Now, we're asked to find the points of inflection, and of course the word point indicates that it should be a point and not just the x coordinate. So the points of inflection are, one of them is at x equals 0, so the y coordinate will be f of 0, whatever that is, and at 2, comma f of 2, whatever that is. So I have to calculate those. So substituting 0 into the original function, 0 to the 4th minus 4 times 0 cubed is 0. And substituting in 2, 2 to the 4th minus 4 times 2 cubed is make sure I don't make a mistake. 2 to the 4th is 16. 2 cubed is 8. 4 times 8 is 32. 16 minus 32 is negative 16. I sure hope I didn't make a mistake on that. Yeah. I don't think I made a mistake, but anyway, I'm pretty sure I'm right. I'll just let it be. Okay. So, all right. So, let's see what is next. Now, if you look at Theorem 3.8, which is similar to an earlier theorem for the first derivative, if c comma f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime of c does not exist. And I think I already mentioned that the converse of this isn't true. Just because the second derivative equals 0 or doesn't exist doesn't necessarily mean that you'll have a point of inflection. So you've got to be careful about that converse. It's not always necessarily true that the converse is going to give you a true statement, so be careful. For example, it's always good to have an example. If I had f of x equals x to the 4th, whose first derivative is 4x cubed, and whose second derivative is 12x squared, and I set that equal to 0, or f double prime doesn't exist. That never happens. Every number can be substituted in for x there, and it's not a problem. And the only answer for this is 0. And so just because that's equal to 0, please don't think that that implies that you have to have a point of inflection. Because if you look at the second derivative, 12x squared, if I put in a negative number like negative 2, the square of negative 2 is positive 4. 12 times 4 is positive. And if I put in 3, 3 squared is 9. 9 times 12 is a positive answer. And this is concave upward, and then concave upward. No point of inflection. And if we look at the graph of that function, that should totally make sense to us, because this graph, although not a parabola, kind of reminds us of a parabola. Well, looks sort of like that. And on the left side of the y-axis, it's concave upward, and on the right side, it's also concave upward. Even though the second derivative equals 0 at 0, it is not a point of inflection. Okay, so I'm going to need to end this particular recording and go to part 2. So I'm going to end this and start a new one.